The derivative is defined as f prime x equals to limit of f of x plus h minus f of x all over h as h tends to 0. I'll apply it to the first two examples we looked at from before. First, there was the straight line equation we had where fx equals to 2x plus 8, whose gradient we know is 2. So we can try derive the derivative equation, then just sub in the x value of 1. This was the derivative equation where fx plus h is 2x plus 2h plus 8. Then sub this back into the derivative equation, which just leaves 2h over h. Then the h's cancel off, leaving 2. And even though the h from the denominator is gone, we don't have any h's left to sub in h equals to 0. So the derivative just ends up as 2. And we need to get the gradient when x equals to 1, which, since there's no x terms, just comes out as 2 again. This wasn't surprising, given that the gradient of a straight line is constant, so it isn't affected by what x's value is. Let's try again for the second example. For the equation y equals to 3x squared, what's the gradient when x equals to 4? So fx is 3x squared, and the derivative equation is, then fx plus h comes out as 3x squared plus 6hx plus 3h squared. Then sub it back into the equation, and the two 3x squareds would cancel each other out. You can now factorize out the h in the numerator, and the h's cancel out, leaving it as 6x plus 3h. And since the h from the denominator is gone, we can now sub in h equals to 0. And this finally gives the derivative as 6x. Then to get the actual gradient value at x equals to 4, we just sub in x equals to 4 into the derivative equation, and finally get the gradient as 24. Okay, cool, we got the same answer again. That's nice, but what was the point? We still pretty much had to do the same amount of writing. Okay, just stick with me here. It's all going to lead somewhere. Before I move on to another example, there's some important notation for you to be aware of. The derivative represents an equation you can use to determine the gradient at any point on a curve. Earlier on, when I introduced the derivative equation, I represented it using the notation f with a sort of apostrophe next to it. I didn't really use this notation in the two examples I covered because I just wanted you to first see it in action before introducing new terminology. But from now on, I'll use this and other terminology which are very important for you to learn and keep in mind. So I suggest write these somewhere on the side in red so you can refer to them later. So the first of these is this f apostrophe term, which is read as f prime x. And here's a few other terms which mean the exact same thing. One is y prime, which I guess makes sense because fx and y are often used interchangeably. Then a completely new one is dy over dx, whose full form is read as derivative of y with respect to x. Another one is d of x, which also means the same thing. And the last is df over dx, which is similar to dy over dx, but the y is just replaced with f. I'll use these different forms at different points during this video and just assume you know what they mean. That being said, here's a new example for derivative. If y equals to minus 5 over x plus 2, calculate the derivative dy over dx from first principles. Notice the different language used. This time, they ask for the derivative instead of asking for the gradient at a particular point. So they don't want some value, but actually an equation. Also, they indicated the derivative using dy over dx instead of f prime. And lastly, they said from first principles. What that means is using this derivative equation, there's different ways of determining the derivative. One is using this equation, and the other one I'll cover in some time. So when they say using first principles, they mean using this equation. Therefore, this equation is quite important, but you don't need to know it by head. it will be given in the formula sheet you get with your exam paper. Coming back to the example, we need to find the derivative of y equals to minus 5 over x plus 2. So dy over dx would be equal to the derivative equation. Fx is just y, which is minus 5 over x plus 2. Then fx plus h is equal to minus 5 over x plus h plus 2. Then just sub these back into the equation, and these two negatives cancel out to just give a positive. Then you add the two fractions in the numerator how you normally would using the lowest common denominator. Then multiply out the 5's and the bracketed terms. Then in this very top numerator, the 5x's and the 10's will cancel each other out, leaving just 5h. Then the h in this numerator can cancel out with its denominator at the bottom, giving 5 over x plus h plus 2 times x plus 2. And since you've cancelled out the h in the denominator, you can now sub in h equals to 0, finally giving the derivative as 5 over x plus 2 squared. This whole process of determining the derivative of a function is known as differentiation. Let's move on to the next section, which is differentiation rules. So as earlier mentioned, determining the derivative using the derivative formula is quite a long process, but whatever the case, the goal is to end up with an equation having x terms in it. Turns out, depending on the form of the original function you're differentiating, some trends were noticed related to what form the derivative would end up having, and from this, some differentiation rules were determined that tell you how the derivative will look depending on how the function looks. And the benefit of this is that it allows you to get the derivative equation without having to go through the whole long process with the x plus h and so on. The first of these is a general rule of differentiation, which states that the derivative of x to the power of n is equal to n times x to the power of n minus 1, where n is any real number except for 0. Let's apply it to an example. Differentiate the following using first principles and using the general rule of differentiation. So the question asks us to differentiate using first principles, meaning using the derivative equation with the h's and everything, and also using the general rule of differentiation I just talked about. The point of this example is to show you that you will indeed end up with the same result, but with much less effort using the general rule. So the function we need to differentiate is fx equals to x to the power of 5. First, I'll do it using first principles. That's the differentiation by first principles equation we've been using from before. Till now, I've referred to it as the derivative equation, but it's actually known as the equation for differentiation by first principles, and that's what I'll be calling it from now on. First, let's determine f of x plus h, which would be x plus h to the power of 5. That's going to be a pretty long multiplication, so I'll just do it by myself and give you the answer. If you want to, you can do the multiplication by yourself, but whatever the case, you get h to the power of 5 plus 5h to the power of 4 times x plus 10h cubed times x squared plus 10h squared times x cubed plus 5h times x to the power of 4 plus x to the power of 5. Then sub it back into this equation. Then the x to the power of 5 terms would cancel each other out, but everything else would remain. Then you factorize h out of the numerator, and the h's cancel out, leaving h to the power of 4 plus 5h cubed times x plus 10h squared times x squared plus 10h times x cubed plus 5x to the power of 4. Since you cancelled off the h from the denominator, you can now sub in h equals 0. And if you do that, basically all these terms with an h in them will just turn to 0, leaving behind just 5x to the power of 4 as the derivative. So that's differentiation using first principles. Then let's use the general rule of differentiation. That's the equation to be used, but first we need to compare the two forms. This one on the right means if you differentiate a function of the form x to the power of n, you get n times x to the power of n minus 1. In this case, the function is x to the power of 5, so n equals to 5. Then using the general rule, the derivative would be n, which is 5, multiplied by x to the power of 5 minus 1, which gives the derivative as 5x to the power of 4, which is the same as what we got using the first principles method, but with so much less effort. Here's another example. You now need to differentiate the following using the general rule of differentiation. First is x cubed, for which n equals to 3. Then, when you apply the equation, you get the derivative as 3x squared. Next is part b, which is x, for which n would be equal to 1. Then using the equation, you would end up with an exponent value of 0, which just gives the value as 1. Last, we have x to the power of 1, 5, for which n equals to 1, 5. As earlier mentioned, the exponent just has to be a real number, so it doesn't need to be a whole number. It can be a fraction, it can be less than 1, it can be negative. The rule still applies. And when you use it, you get 1, 5 times x to the power of 0, 5. And x to the power of 0, 5 is the same as root x. So you can just write it using the square root sign. So I've shown you the general rule of differentiation. Then there's 3 other rules you need to learn that will allow you to differentiate many other different types of functions besides just x to the power of n, starting with rule 1. What it states is that the derivative of a constant times a function is equal to the constant times the derivative of the function. So k just represents a constant, which is just some number. Here's some examples using rule 1. We need to differentiate the following functions, and all of these are pretty much the same functions as the previous example, but this time they have a constant in front of the x term. So you need to use rule 1 to differentiate them. Part A, we need to differentiate 3x to the power of 5. So k, which represents the constant, would be equal to 3. And f of x would be equal to x to the power of 5. So we're differentiating 3 times x to the power of 5. This dot in between is just used to show them as separate terms multiplying each other. Using rule 1, this ends up being 3 times the derivative of x to the power of 5, which from the previous example we found to be 5x to the power of 4. And 3 times 5x to the power of 4 gives 15 times x to the power of 4. Then for part B, we need to differentiate negative 2x. So k would be negative 2 and f of x would be x. So this would be negative 2 times derivative of x, which was just 1 in the previous example. So the final derivative is just 2. Then part C is square root of 2 times x to the power of 1, 5, where k is root 2 and f of x is x to the power of 1, 5. This time we're differentiating root 2 times x to the power of 1, 5, which would just be root 2 times derivative of x to the power of 1, 5, which was 1, 5 root x in the previous example. So the final answer is 1, 5 root 2 times root x. If you wanted, you could further simplify this 1, 5 root 2 term, but it's not a must, and it would be sufficient to just leave it like this. Then part D is 6 times x to the power of 23, which is actually a completely new example, so we'll need to apply both the general rule and rule 1 to get the final answer. N would be the value of the exponent, which is 23 this time, and k is the constant, which is just 6. And f of x is x to the power of 23. We are differentiating 6 times x to the power of 23, which is 6 times derivative of x to the power of 23, so 6 times 23 times x to the power of 23 minus 1. which finally gives the answer as 138 times x to the power of 22. A simple conclusion that can be made from rule 1 is that differentiating a function that's multiplied by a constant doesn't do anything to the constant. It just remains the same and multiplies whatever the function's derivative is. From this conclusion, we can combine the general rule and rule 1 to give a new general rule, which says that the derivative of a constant times x to the power of n equals to the constant times, brackets open, n times x to the power of n minus 1, close brackets. Cool. Then let's look at rule 2. Rule 2 says that when you differentiate a constant, you get an answer of 0. In other words, the derivative of a function that's just a number, for example, y equals to 2, the gradient of that would just be 0. Here's an example. Differentiate the following. For part A, we need to differentiate -2, and using rule 2, we can just say that the derivative of -2 will simply be 0. Then for part B, we need to differentiate square root of 2. And when we apply rule 2 to this, again, we just get the derivative as 0. I could go through some more examples, but it will just get pretty repetitive because it's the exact same process over and over. If we have to find the derivative of a constant just by itself, with no variable attached to it, you will always get a value of 0. Pretty simple, right? That's all there is to know about rule 2. And finally, let's look at rule 3. This rule says that when you take the derivative of a sum or a difference of functions, this will equal to the derivative of one plus or minus the derivative of the other. Put more simply, the derivative of a sum equals the sum of the derivatives, and the derivative of a difference equals the difference of the derivatives. Let's look at an example. Find the derivative of the following. For this one, I chose different combinations of various functions we've already seen. I'll just put rule 3 here on the side so you can refer to it. For part A, it's x cubed plus x. You can call x cubed as f of x and x as g of x. The derivative of the sum of functions is equal to the sum of the derivatives of the functions. Earlier on, we saw that the derivative of x cubed is 3x squared and the derivative of x is just 1. So the final answer is 3x squared plus 1. For part B, it's x to the power of 1, 5 minus x to the power of 5. X to the power of 1, 5 can be f of x, and x to the power of 5 can be g of x. So the derivative of the difference of these two functions equals to the difference of the derivatives. We saw earlier the derivative of x to the power of 1, 5 is 1, 5 root x, and the derivative of x to the power of 5 is 5x to the power of 4, giving the final answer as 1, 5 root x minus 5x to the power of 4. For the next example, let's go up a level and look at the sum or difference of various functions, each of which has coefficients. For part A, you need to differentiate the function I of x equals to 50x cubed plus 3x to the power of 5 minus 3,419. So I prime x equals to derivative of this whole function, which equals to derivative of 50x cubed plus derivative of 3x to the power of 5 minus derivative of 3,419. Then we can take the different coefficients out, giving 50 times derivative of x cubed plus 3 times derivative of x to the power of 5 minus derivative of 3,419. We know that the derivative of x cubed would just be 3x squared. The derivative of x to the power of 5 would just be 5x to the power of 4. And the derivative of 3,419, which is just a constant, would be 0. Finally giving I prime x as 150x squared plus 15x to the power of 4. For part B, we need to differentiate the function f of q equals to 2 over root q. Remember that it won't always be x as the independent variable. It could be anything. This time it's q, so you have f of q. So df over dq would be derivative of 2 over root q with respect to q. It's still not simplified enough to directly differentiate it. My best advice, especially related to when you have to differentiate something with a funny variable in the denominator, is to first represent the power in as basic a form as possible and then bring everything up to the same level, meaning bring the denominator terms up and make the power negative. And only once you've done that should you go about differentiating them using the various rules. So in this case, first you change the square root sign to a power of half. Then bring it up, giving it as 2 times q to the power of negative half. Now we can apply the different rules. First, the term has a coefficient, so we can bring it out. Then apply the general rule, bringing down the negative half and subtracting 1 from the power. And this finally gives the answer as minus q to the power of minus 1.5. And if you want, you can bring the negative power back down as a denominator, giving df over dq as minus 1 over q to the power of 1,5. At this point, we've covered all the differentiation rules to know and use them in various situations. So just to make sure you're on point with it, I'll give 2 final tough examples. For these, I'll state the question, then you should pause and try it out, then I'll just post a full working and you can go through it in your own time. So for the question, you need to differentiate the following functions with respect to z. For part A, it's q as a function of z equals to 21 times root z minus 4.5 over cube root of z. Pause and try it out. Here's the full working, giving the final answer as dq over dz equals to 10,5 over root z minus 1,5 over z to the power of 4 over 3. Then for part B, you need to differentiate f as a function of z equals to z plus 5 squared times z plus 1 all over square root of z. So this is an extra step beyond any examples I showed you so far, but very similar to something you could see in a test or an exam. Before posting the working, here's some advice. Try expand everything and then divide. Pause and try it out. Here's the working. First, I expanded z plus 5 squared, and then I multiplied out everything in the 2 brackets. Then I added together similar terms, and once that was done, I divided each separate term by the z to the power of 0,5 in the denominator. After that, it's just application of the new general rule I derived, finally giving the answer as 2.5 times z to the power of 1.5 plus 16.5 root z plus 17.5 over root z minus 12.5 over z to the power of 1.5. We can now move on to the next section of the topic, which is equations of tangents.